Hello again, everyone. Welcome to our discussion of the algebra of matrices. What we're talking about here, last time we learned how to solve a system using the Gauss-Jordan method or using the matrices. Today, in this section, we will learn about how to add, subtract, multiply matrices, or multiply matrices by each other, or multiply a matrix by a number. Okay, today we will learn about that. Before we get into that, I'd like to remind you all to please read through this textbook section, and before you watch this video or attend class, then take notes throughout the video in case you have a question about the stuff I talk about, or as you read the textbook, then make a note of things that you have questions about or things that you think are important to your learning the content. And then, of course, review your lecture notes and solve all the problems you see in this video or in the textbook section on your own without looking at the solutions we show. And, of course, complete all the homework by the due date and then review all the previous material, because this mathematics subject is cumulative in nature. Okay, so the algebra of matrices, we're going to start with something easy, such as adding two matrices. One thing that we should make sure of is that only matrices of the same size may be added or subtracted. And last class we talked about the matrix size or dimension, right? The size or dimension of a matrix is the number of rows times the number of columns. So for example, this matrix is a 2 by 2 matrix. It has 2 rows and 2 columns. This one is a 2 by 2 matrix, 2 rows and 2 columns. Okay, we can look at these two before we solve this. We can look at these. So this is a 2 by 3 matrix, which is in a subtraction operation with another 2 by 3 matrix. So what that statement is saying that only matrices of the same size can be added or subtracted. Okay, matrices that have various sizes cannot be added or subtracted by each other. Okay, so looking at that, we just add the equivalent terms in both matrices. So this is equal to minus 11 plus minus 8, right? Then 3 plus 6, 2 plus 10, minus 7 plus 7. Okay, let's simplify this. Minus 11 plus minus 8, we get minus 19. 3 plus 6, we get 9. 2 plus 10, 12. Minus 7 plus 7 is, of course, 0. Okay, that's adding two matrices. Subtracting, once again, the matrices that we're subtracting have the same size. Okay, so that's a valid operation. So 0 minus 2. 2 minus 6. 9 minus minus 5. 7 minus 8. 7 minus 2. 0 minus minus 4. Right? And then we'll simplify this. And we get 0 minus 2 is minus 2. 2 minus 6 is minus 4. 9 minus minus 5. This will make this positive. So 9 plus 5 is 14. 7 minus 8 is minus 1. 7 minus 2 is 5. 0 minus minus 4. That's 0 plus 4, which is 4. Okay. So now, multiplying a matrix by a scalar. A scalar is a number. It's just I use this terminology intentionally to make sure that you've at least seen this once and you know what it means. A scalar is a number, a constant value, a number like 2 minus 1/2, something like that. So in this case, the scalar or number is minus 6. We want to know how to multiply this number by this matrix. Well, we simply multiply each term by that number. Or in other words, we distribute negative 6 into each term. Okay? So we have minus 6 times 10, minus 60. Minus 6 times minus 4, positive 24. Minus 6 times minus 8, positive 48. Minus 6 times 3, minus 18. Minus 6 times 0, 0. Minus 6 times 0, 0. Okay? And we are done with that. Okay. Now, multiplying two matrices is a different ballgame. In fact, in some textbooks, this topic has its own section, separately than what we just discussed, operations involving matrices. But in this textbook, it's mixed, which is fine. It doesn't matter. We still have to cover it. So suppose we have two matrices A and B, right? Naturally, each of these matrices has a dimension or size, right? So just like with the operations adding or subtracting matrices, where matrices had to have the same size, the size of matrices here does matter, but it's not the same rule as we discussed when adding or subtracting matrices. So let's see how the size of a matrix matters when we multiply two matrices. So the product of two matrices A and B is not the same as multiplying B times A. This is very important for you to understand, because in basic algebra, in regular mathematics, when you multiply two numbers, if you say 2 times 5, it's the same thing as 5 times 2. If you say negative 2 times 3, it's the same thing as 3 times negative 2, right? The result is not going to be different if you change the order. But when you multiply matrices, A times B will lead to a totally different result than B times A. There are special cases, but so far we're not going to look at those very, very few special cases, such as multiplying a matrix by the identity matrix. The order doesn't matter in that case, but that's a special case, and in this course we're not going to look at that. In most cases, in the vast majority of cases, probably 99% of cases, when we multiply matrices, the order of multiplication does change the result of the product. So in fact, it can be that A times B is possible, but B times A, multiplying matrices in that order, is not possible. Okay, so that's even possible. And not only the results are not the same if you change the order of multiplication when you deal with matrices, but also in one case you might have a result, and in the other case you may not even have a result. Okay, so this means that A times B is not equal to B times E. This also means that the order of multiplication of matrices matters. One product may be possible where the other product may not be, which is just what I just said. So the product A times B, matrices multiplied in this order, is only possible if matrix A has the same number of columns as there are rows in matrix B. So only if if you're multiplying A times B, suppose A, matrix A, has 3 columns. Then B had better have 3 rows. So it should have the same number of rows as the number of columns in matrix A. If it doesn't, if the columns in A are not equal to number of rows in B, then this multiplication cannot happen. It is not possible. Okay? So suppose matrix A has dimension k times m. That means matrix A has k rows and m columns, and matrix B has dimensions m times r, right? That means the matrix B has m rows and r columns. Therefore, the product matrix has dimension k times r. There are 2 things happening here. One is the product possible? Second, what is the size? If the product is possible, what is the size of the resultant matrix? Okay, so we just mentioned that in order for multiplication to be possible, we must have equal number of columns in the first matrix as number of rows in the second column. That's the condition for being able to multiply 2 matrices. Then the next question is, okay, if we can multiply 2 matrices, what is the size of the resultant matrix? Okay, the resultant matrix will have the same number of rows, not columns, the same number of rows as A and the same number of columns as B. Okay, and I've explained it in under number 3 in words, and this diagram is showing what is mentioned in that paragraph above it. Okay, so matrix A, k times m, right? So matrix A has k rows and m columns. Matrix B has m rows and r columns. Notice the number of columns in A is equal to the number of rows in B. So m equals m. That means the product is possible because the number of columns in the first matrix is equal to the number of rows in the second matrix, right? M and m. So product is possible. Now, what is the size of the product matrix? The size of the product matrix is k times r. So you take the number of rows from the first matrix and multiply it by the number of columns in the second matrix. But this one, the number of columns in the first matrix and the number of rows in the second matrix determines whether the multiplication is possible. Okay? I can't emphasize more. 2 things are happening here. Whether check to see if the product is possible. Second, if the product is possible, what is the size of the resultant matrix? Okay? So, the product of 2 matrices begins by multiplying the elements in the first row of the first matrix by the elements of the first column in the second matrix, while adding the results together to obtain the first element in the matrix. Okay, in this short paragraph, I'm writing in words because some of you might prefer that. Some of you might prefer to read what's involved when multiplying 2 matrices. But also I will explain in numbers what is happening here. So what this paragraph is saying is that once you verify that, as a matter of fact, let's see if this product is possible, right? So the first matrix is 2 by 2, right? That one. What about this matrix? This matrix has 2 by 3, right? 2 rows and 3 columns, 2 rows and 2 columns, right? So take a look at the number of columns in the first matrix and compare it with the number of columns in rows in the second matrix. So we have 2 equals 2, so the matrix multiplication can in fact happen. Okay, so the question now is, what is going to be the size of the product matrix? Well, the size of the product matrix, take a look at these two numbers. The number of rows in the first matrix and the number of columns in the second matrix. So the resultant matrix will be a 2 by 3 matrix. Okay, so we perform the check very quickly, mentally. We perform a check to make sure that these two matrices can be multiplied. If they can, then the size of the resultant matrix is going to be a 2 by 3 matrix. Okay, so we already know that. Now, how do we multiply? The way we multiply matrices is we start by multiplying these numbers in the first row of the first matrix by each of the columns in the second matrix, and then add the result for each column. So multiply 8 by 2 and then 2 by 3 and add them together. So 16 plus 6, 22, right? Once you're done doing that, you multiply the same row by the second column in the second matrix. When you're done that, adding the numbers, multiplying and adding, then you multiply the first row by the last column. When you're done, when you run out of columns, you do the same thing again, but this time with the second row, going through column by column in the second matrix. Okay, so let's do that. So I'm going to put that resultant matrix here. And we know it's going to be a 2 by 3 matrix, right? This one. So 2 rows and 3 columns, just like this one. Okay, so 8 times 2 plus 2 times 3. Okay, so I multiplied the first row in the first matrix by the first column in the second matrix. Now let's multiply the first row in the first matrix by the second column in the second matrix. So 8 times negative 1 plus 2 times 2. Okay, so we're done with that column. Let's move to the third column. 8 times negative 4 plus 2 times negative 7. That's a 2 under my red ink there. That's a 2. 2 times negative 7. Okay. Then we run out of columns, right? 1, 2, 3. We're done. So let's move to the second row in the first matrix and repeat. Multiply by first column, add the numbers. Multiply by the second column, add the numbers. Multiply by the third column and add the numbers. Okay, let's do that. So minus 2 times 2 plus 1 times 3. Right? We're done with the first column. Multiply the second row by the second column. Minus 2 times minus 1 plus 1 times 2. Okay, we're done with the second column. Let's move to the third column. Minus 2 times minus 4 plus 1 times negative 7. Okay, now let's simplify. So equals. We have 8 times 2 is 16 plus 6, 22. 8 times negative 1 is minus 8 plus positive 4. That's negative 4. 8 times minus 4 is minus 32. Minus 32 plus minus 14. Right? So it's going to be minus 32 minus 14. That'll be minus 46. Right? 14 plus 32. That's correct. Okay, for minus 46. Then, minus 2 times 2 is minus 4, plus 3, minus 1. Minus 2 times minus 1, positive 2. Plus 2, 4. Minus 2 times minus 4, positive 8. Plus minus 7. 8 minus 7 is 1. Okay, and we are done with that. Like that. Okay. We have more examples of multiplying matrices. So this one, we want to multiply this matrix by this one. Let's check to see if this product is possible. So we have 2 by 3 matrix here, right? 2 rows and 3 columns. How about this one? This one is 3 by 2 matrix, right? That's the size of this one. So compare the columns in the first matrix with the number of rows in the second matrix. Are they equal? They're equal. So multiplication is possible. Now that we know this product is possible, what is going to be the size of the resultant matrix? Okay, so let's see that number, two rows and 2 columns. So it's going to be, the resultant matrix is going to be a 2 by 2 matrix. Okay, that's the size of the resultant matrix. Okay, so let's do what we did before and take the first row, multiply it by the first column and then the second column and add the numbers together. Okay, let's do that here. So 2 times 1 plus 1 times 3 plus 2 times minus 2. Right? We finished multiplying the first row by this first column. So we multiply the first row by the second column now. Okay? So 2 times minus 2 plus 1 times 6 plus 2 times 0. Okay, we've run out of columns in the second matrix. What do? We move down to the next row and repeat the procedure. So 6 times 1 plus 3 times 3 4 times minus 2. Okay, we're done with this column. Now we multiply the second row by the second column. So 6 times negative 2 plus 3 times 6 plus 4 times 0. Okay, so let's simplify. We have 2 plus 3, 5, minus 4, that is 1, right? 5 minus 4 is 1. Adding all of those algebraically. This one, 2 times minus 2 is minus 4, plus positive 6, that's positive 2, plus 0 is just 2. 2 plus 0 is 2. Okay. Here, 6 times 1, 6. Plus 3 times 3, which is 9. So 6 plus 9 is 15. Minus 8. 15 minus 8 is positive 7. 6 times minus 2, that's minus 12, plus 3 times 6, which is positive 18. So minus 12 plus positive 18. Right? That's positive 6. Positive 6 plus 0 is just 6. Okay? All right. So, which is the 2 by 2 matrix that we anticipated, right? Okay. So let's look at these two, the product of these two matrices. Let's check and see if this product is possible. So the first matrix is, what is the size of this matrix? It is 3 by 2. Right? How about this one? That matrix is 2 rows and 1 column, right? So that's a 2 by 1 matrix, the second one. So notice the number of columns in the first matrix is equal to the number of rows in the second matrix. So it checks out. We can actually multiply these two matrices, even though it looks odd, but the multiplication is possible. Okay, so now the question is, what is going to be the size or dimension of the resultant matrix? Okay, so that'll be, take this number and that number. So the resultant matrix will have 3 rows and 1 column. So it's going to be a 3 by 1 matrix. Okay. Okay, so let's perform the product. Just as before, we take the first row, multiply by the column, and add the numbers. Because there's no other column after that, then we move to the second row and repeat. And because of that, then we move to the third row and repeat, and we end up with that anticipated matrix which has size 3 by 1. Okay, let's do that. So 2 times 5 plus minus 3 times 1. We have 2 more rows to go, right? It's a 3 by 1 matrix. So 3 rows and 1 column. 0 times 5. So we're moving down 1 row, right? 0 times 5 plus 1 times 1. We're done with that row, and we ran out of columns, right? So we move down another row until we're finished with all the rows, right? 1 times 5 plus 2 times 1. Okay, that is equal to, let's simplify, 10 minus 3, 7. 0 plus 1, 1. 5 plus 2, 7. Okay, so this is our 3 by 1 matrix, 3 rows and 1 column that we anticipated. I hope this is making sense. And if you read the book before you watch the video, for sure it'll make sense. Okay. Okay, so we have this example. Once again, let's see if it's possible for us to multiply these two matrices. The first matrix has 2 rows and 3 columns, right? So this is a 2 by 3 matrix. The second matrix, it has 3 rows and 3 columns. So it is a 3 by 3 matrix. So the number of columns in the first matrix is equal to the number of rows in the second matrix. It checks out. We can multiply these two matrices. Okay. If you switch the order, if you put this matrix first and then second, I'm sure you'll see that the number of columns and the number of rows will not match. So if you switch the order if you put this matrix first and that one second, the product is not going to be possible. But in this order, the product is possible. So the next question is, okay, what is going to be the size of the product matrix? Well, take this number, 2, multiply by the number of columns in the second matrix, and we're going to have 2 by 3 matrix. So the resultant matrix, when we're done, it's going to have 2 rows and 3 columns. Okay? All right, so once again, we start with the first row. Let's multiply column by column by column and add the numbers as we go, right? So we have 2 times 3 plus 3 times 1 plus 1 times 2. We're done with the first column, right? We're done with this. We're going to move to the second column. 2 times 4 plus 3 times 1 plus 1 times 1. Okay, we're done with the second column. We're going to move to the third column. So, 2 times 5 plus 3 times 4 plus 1 times 4. Okay, we ran out of columns. What do we do next? We move 1 row down in the first matrix to that one, and we repeat the procedure. So, 2 times 3 plus minus 7 times 1 plus 4 times 2. Like that. We're done with the first column. We're going to multiply the second row by the second column. So 2 times 4 plus minus 7 times 1 plus 4 times 1. Okay, we're done with this column. We move to the third column. 2 times 5 plus negative 7 times 4 plus 4 times 4. Okay, like that. All right. The screen looks a little bit out of focus. Let me try to focus it. Okay, that's better. Okay. So simplifying, we have 2 times 3 is 6. 6 plus 3, 9. 9 plus 2, 11. 2 times 4 is 8. 8 plus 3, 11. 11 plus 1, 12. 2 times 5 is 10. 10 plus 12, 3 times 4, 12, plus 10, 22. Right? 10 plus 12, 22, plus another 4, 26. 2 times 3, 6. Minus 7, that's minus 1. Plus 8, minus 1 plus 8, it's positive 7. 2 times 4, 8. Minus 7, 8 minus 7 is 1. 1 plus 4 times 1, 5. 2 times 5, 10. Minus 7 times 4, that's minus 28, plus 10. Minus 28 plus 10 is minus 18. plus positive 16 minus 2, and we're done. Okay? As you're done with this video, then redo the examples that are solved in the book without looking at those solutions, and redo these without looking at my solutions, and if you can get these results, you are in very good shape. So, and that goes for all the sections I've covered so far. So thank you for staying along in this video. Have a nice day, and I'll see you again next time.